This is a video on the integral test. The question states, determine if the series converges or diverges. And we have the summation n equals 0 to infinity of 2n plus 1 over n squared plus n plus 1. So what's nice here is that the derivative of the denominator is equal to the numerator. So that gives us a hint that the integral test might be what we need to use. But to use the integral test, we have to show that first, the function is bounded. So if we take 2n plus 1 over n squared plus n plus 1, we need to make sure that's bounded. Well, first thing is that for all positive n, this is clearly not negative. No, there's no negatives here. So it's greater than 0. And in particular, if n is 0, we start at 1 and then we stay up. Then we can look at this and say, what about n being very large? Well, in particular, if n is, 10 or so, this n squared is much bigger than the 2n plus 1. So in particular, I can say that the denominator is larger than the numerator for large enough n, and it turns out all you need is n bigger than 1. So in particular, this fraction is less than 1. So therefore, 2n plus 1 over n squared plus n plus 1 is bounded between 0 and 1. We also have to show that the function is decreasing. So to do that, I'm going to use calculus. I'm going to take a derivative of this function. Just to make it easier, I'm going to call it x instead of n. We're more used to that. And we can look at the derivative of 2x plus 1 over x squared plus x plus 1. And I use the quotient rule. So that says the low, x squared plus x plus 1, times the derivative of 2x plus 1, which is 2, minus the high, which is 2x plus 1, times the derivative of the low, which was 2x plus 1. Derivative of x squared is 2x, the derivative of x is 1, so there's the 2x plus 1, divided by the bottom squared. So now we just have to show that this is negative, because if the derivative is always negative, then we know the function is decreasing. So I just kind of multiply the numerator through and combine like terms. I'm going to spare you the mess. And what I got is negative 2x squared minus 2x plus 1. And then we still have the denominator squared. Notice anything squared can't be negative. It's got to be positive as long as you're bigger than 1, which we are. So we just have to show that the numerator is negative. But for large n, that's all we care about, or large x in this case, we have negative 2x squared minus 2x plus 1, and the negative 2x squared is a dominating term. So this is definitely negative for x large. And it turns out as long as x is bigger than 1, we're good. So now we can conclude that our sequence 2n plus 1 over n squared plus n plus 1 is bounded and decreasing, which means I can use the integral test that says that the integral converges, the series also converges, and if the integral diverges, the series also diverges. So now let's integrate. I'm going to call it x instead of n because we're more familiar with that. And I'm going to take the integral from 1 to infinity. I can choose any number here. I'm going to choose 1 because it's easier. It's the infinity that matters. Of 2x plus 1 over x squared plus x plus 1, I can use u substitution. Let u equal the denominator, x squared plus x plus 1. Then du is 2x plus 1 dx. And notice that we have 2x plus 1 dx right here. So this integral becomes du over u. And notice if x is 1, 1 plus 1 plus 1 is 3. So I have a 3 down here. And if x is infinity, infinity squared plus infinity plus 1 is also infinity. So we get the integral from 3 to infinity of du over u. Well, that's an easy integral. That's a natural log. So we take the natural log of u from 3 to infinity, and now let's plug in. And what we get is the natural log of infinity minus the natural log of 3. But the natural log of infinity is infinity. And the natural log of 3 is just some number. So infinity minus some number is infinity. And that tells us that this integral diverges. We're ready to state our conclusion. And the conclusion is the series diverges by the integral test. And I'm done with the problem.